geometrical interpretation of grad phi. The term is level surfaces. If phi is uniformly continuous scalar point function, then the locus of the point P such that phi P is equal to phi A. Now the locus of the point P such that these two are equal. At the point P, the value is equal to the value at the point A, right? Such the locus of the point is forming there, having this blue curve. This is your locus of the point P such that this phi P is equal to phi A, where A is any given point. This is called the level surface of phi through the point A, right? Now this surface is such that you have to take the value of the function at any point is same as that of A. Suppose you have taken another point B, then the value for the function at A is equal to the value for the function at B, which means the level surface for any point A is the level surface for any point B of the surface, right? So from here we get some points. The direction cosines of the two sides of the normal at A point to the level surface phi r. Now this is your level surface, this curved one, and this is your normal which is drawn perpendicular to this level surface having the point A, having the coordinates x, y, z. Now we have to calculate the direction cosines for this normal. And the direction cosines of the two sides, the upper and the lower side, is phi x over root of summation phi x square. Summation phi x square means it is phi x square plus phi y square plus phi z square, comma, then phi y over root of phi x square plus phi y square plus phi z square, right? Then the third one is phi z over root of summation of phi z square, which is one and the same thing. All the denominators are same, right? So take this as your 1. These are the direction cosines. That is, this is your L, this is your M, and this is your N, right? And also the negative one also, right? Because for the lower side, this will be minus phi x over root of summation phi x square and minus phi y by root of summation phi y square, then minus phi z over root of summation phi z square. Again, I am saying that summation phi x square is equal to summation phi y square is equal to summation phi z square, which is one and the same thing, that it is under root of phi x square plus phi y square plus phi z square, right? Now, the second point is the directional derivatives of the function phi along these two sides are. Now I have to write the directional derivatives of the function along the two sides, means I am writing along the line, and we have studied before in the previous video that the directional derivatives of the function phi along the coordinate axes are phi x, phi y, phi z. But if we study the directional derivatives of the function phi along the line, then that will be the sum L phi x plus M phi y plus N phi z. So this is your directional derivative along the line. So now calculating this, putting the value of L over here, I get. Okay, let me take a blue color pen. So this is, put the value of L over here, which is phi x over root summation phi x square, and I'm having this phi x also plus M. This is phi y over root of summation phi y square phi y, then plus phi z over root of summation phi z square, and I'm also having this phi z. Now if you sum up this, because denominators are same, so the numerator will be phi x square plus phi y square plus phi z square. Can I write it as summation phi x square? Yes. Divide by root of summation phi x square, which is further equal to, now this is the root. This is further equal to root of summation phi x square, right? And this is nothing but, what is summation phi x square? This is your, this root, this is your gradient phi. Why? Why gradient phi? Because we know that grad phi is what? I curly phi over curly x plus j curly phi over curly y plus k curly phi over curly z. What is curly phi over curly x? This is phi x, right? Let me write that. Let me explain over here only. Now see, what is your grad phi? Alright. I explain you why this is equal to grad phi mod. See, your grad phi is equal to I'm using the word del for this, but I have to use the word curly for this because del is same as that of the del operator. This, just to make the difference, I use the word del for this operator and I use the word curly for this sign, right? It is also pronounced as curved D, or it is rounded D, or Daba, or Jacobi's delta. You can also say it as del or curly. So just to make a difference, I'm using the word curly for this sign and del for this sign. Thank you. So this is plus j curly phi over curly y plus k curly phi over curly z. This is equal to, now curly phi over curly x is your phi x, j, this is your phi y, plus k, this is your phi z. Now if you take the mod for grad phi, what is the mod for grad phi? This is, yes, phi x square plus phi y square plus phi z square under the root, right? So you can also write it as, see, what is the grad of mod of grad phi? This is equal to root of phi x square plus phi y square plus phi z square, which can also be written as root of summation phi x square. This is what we are having. Yes, so can I write instead of this as mod of grad phi here? Thank you. So this is mod of grad phi. Now similarly, if we take the negative direction cosines, then I'm having minus mod of grad phi for the opposite side. Now since the direction derivative mod grad phi along the side of the normal given by 1 is positive, so therefore phi is increasing along this side of the normal. Where the phi is increasing? The phi is increasing along this side of the normal. Now this is very important point. Also we see that direction cosines of the vector grad phi are same as those given in 1. What are the direction cosines for grad phi? Of course, phi x, phi y and phi z. And these are also, yes, no. The direction cosines for grad phi is phi x over root of summation phi x square, right? And the other one is phi y over under root of summation phi y square, phi z over under root of summation phi z square for grad phi. And these are also the direction cosines for this side, the normal side which we have taken from first. See, the direction cosines of the two sides, let me take the positive one. This is same as that of the direction cosines of grad phi. I have explained to you. What is your grad phi? It is... I have to change the color of the pen. Okay, what is grad phi? It is I phi x plus j phi y, because curly phi over curly x is your phi x only. So this is phi z, right? So you can see what are the direction cosines for this grad phi. It is phi x over, yes, summation under root. Do you understand now? I'm talking about root of phi x square plus phi y square plus phi z square, alright? And m is phi y over root of summation phi y square, and n is equal to phi z over under root of summation phi z square. So direction cosines of the grad phi are same as the direction cosines of the normal which we have drawn, a normal which is perpendicular to the level surface. So whenever you need to find the vector normal to the level surface, you just need to calculate grad phi for that. So therefore the vector grad phi is parallel to the side along which phi increases to the normal to the level surface through the point, and the magnitude of grad phi, this mod of grad phi. What is this? This is the directional derivative of phi along the same side, right? Now there is a remark. If a vector is any unit vector, then the dot product, its dot product with grad phi is a directional derivative of phi along the direction of a vector, right? This you need to remember. So we have a vector dot grad phi as, now the dot product can be calculated as mod of vector A mod of grad phi cos of theta, right? And this is further less than equal to your mod of grad phi. Is it? Can I write like this? Alright. Now this is for all the unit vectors A. So thus what it follows from here, that this dot product is less than equal to mod grad phi, it follows that the direction of grad phi at any point coincides with the direction along which the directional derivative of phi is greatest, right? Let's do one example which will make you more clear what you have read in the concept about the geometrical interpretation of grad phi. This example makes you more clear. Find a unit vector normal to the level surface x square plus y square minus z at the point -1, -2, 5. Now the level surface is given to you. You have to find the unit vector normal to this level surface. First we have to find the vector. What is the vector that is normal to the level surface? And from that vector we calculate the unit vector, right? Now the given equation of the level surface is, it is given to us x square plus y square minus z. Now to find the vector normal to this level surface, what we need to find? Grad phi, right? So grad phi is equal to this, we know that. So this is curly phi over curly x, this is 2x plus j. Curly phi over curly y, it is 2y plus k. Curly phi over curly z, it is -1. So this is minus k. So thus at the point -1, -2, 5, grad phi will be, put the values of x, y, z from this point. This will be putting x equal to -1 over here. I get -2 iota, sorry, not iota, I. So this is -2 I vector. Then put the value of y here, -2. This is -4 j. And then it is sorry, this is 1. This will be -k only. There is no z over here. So at this point, I'm having grad phi as -2i -4j -k, right? Now this is a vector. Now the vector normal to the level surface is this. So I'm writing vector normal to the level surface at this point is grad phi, which is equal to this. We have calculated our vector normal to the level surface. Now I need to calculate the unit normal to the surface. From this vector, I will make my unit vector. Before that, just recall, if a cap is the unit vector, then this a cap is equal to a vector over mod of a vector. So I'm having my vector this. So to find the unit vector, what I have to do is I have to calculate this given vector over the mod of the given, the result that we have, get the result for the vector divided by mod of the vector we have found. So unit vector normal to the surface is the vector itself minus k over its mod. Which is equal to -2i -4j -k. Now taking the mod of this, which is 4 plus 16 plus 1. This is root of 4 plus 16 plus 1. Just square this and taking their root, which is equal to 1 over root of 21. 2i plus 4j plus k. With minus sign outside. Right? So this is how I have found the unit normal to the surface. Whenever you have to find the unit normal, just first calculate your vector normal to the level surface, calculate your vector, and then to find the unit normal, you just have to divide your vector with its magnitude, just keeping in mind the formula for finding the unit vector.